All right, let's start in chapter 7. So, chapter 7 is all about integration. We in chapter 6 we were looking at some of the applications of integration, and so we've been doing integration all semester so far. But the focus in chapter 6 was more on setting up the integrals. Okay, and then once we did that, usually evaluating the integrals was not very challenging. Um, in chapter 7, we're going to change our focus a little bit. We're not going to be worried so much about the setup of the integrals, but what we will be doing is building up a few more tools for how to evaluate challenging integrals. Okay, so in 7.1, we're just going to give an overview of what we already know about integration. So there's nothing new in 7.1. It's just a review of some integration techniques that you should know. And in fact, if you look at your textbook, this is page 413 of your textbook. It's like the only page in 7.1 because, like I said, there's nothing new. I think it's maybe the second page of 7.1, and it has a list of stuff that we already know, right? So we already know, like, the power rule. You add one to the exponent, divide by that new exponent, right? Integral of an exponential is just the exponential. Right? Integral of 1 over u is natural log of absolute value of u. So that's, kind of like the basic building blocks. You have integrals of some trig stuff that you should remember and have memorized from back in the day. At the end of chapter 6, so in section 6.9, we went over all these hyperbolic functions, right? And so that was pretty recently. So you should have these things kind of in your memory from just pretty recently. And then we have these other forms. So we had these integrals that ended up being inverse trig functions. So we had sine inverse. So the format of like a sine inverse is 1 over the square root of something squared minus your variable squared, right? For tangent inverse, it's 1 over, something squared plus your variables. So something squared plus your variable squared. And then for secant inverse, we had 1 over your variable times the square root of your variable squared minus something squared. Now, in addition to that, these other formulas, 24 through 28, these also came from 6.9, right? So 21, 22, and 23, those things came from Calc 1, right? Math 65. And so you should have those things memorized from your previous calc class. These formulas, though, these came from 6.9, just the last section that we saw in chapter 6. And remember that these things are all inverse hyperbolic functions, right? So here we're expressing them in their logarithmic form, but you may recall that this is just a sinh inverse, right? So this is sinh inverse, and this one was a cosh inverse, right? And so forth, right? This thing was kind of a weird case. It's where you had like on certain parts of the domain it's a tanh inverse, and on other parts of the domain it's a cotangent inverse, right? But the point is that these things are all hyperbolic functions. Now, if I were you, I wouldn't worry so much about committing these to memory. In fact, there's a remark here that says formulas 24 to 28, right? Readers who did not cover 6.9 can ignore those formulas because we'll develop other methods for obtaining them. And so, so we did cover 6.9, but even still, I wouldn't worry so much about memorizing these formulas because as they say down here, we're going to develop, in this chapter, we'll develop other ways of evaluating these kinds of integrals. Okay, we'll use a method called trig substitution in order to do those. So that'll come a little bit later on. But anyway, but the point is, definitely you should know all of the information in formulas 1 through 23. And then if you also know 24 to 28, that wouldn't hurt, but it's probably not totally essential. Okay, so with that in mind, I just want to run through, I think I have 7 examples that I want to run through with you. So let's get to them. Remember, of course, in addition, so maybe I should say this. So in addition to all of these, various kind of formulas, we also have U substitution as a tool in our toolkit, right? So we have U substitution available to us as well. Okay, so let's get into it. Let's evaluate some stuff. So this first one that we have, the integral of 3 times the square root of 4 plus 2x. So if you can do this in your head without a U substitution, that's amazing. Good for you. I can't. I mean, maybe I could if I really tried, but it's much easier for me if I just write some things down. I'm going to do a U substitution. I'm going to let 4 plus 2x be U, right? So if I can get my pen to write. So let U be 4 plus 2x, and then du is going to just be 2 dx, right? Now, I don't have a 2 dx, I have a 3 dx, but that's not a problem. I can take the 3 out and put a 2 in its place, as long as I offset that by dividing by 2 out there, right? In other words, so I can move the 3, outside of the integral, call it 3. I can put a 2 in its place, as long as I offset that by dividing by 2, right? So now I have 2 dx, right? So so this stuff here, 2 dx, that's du, right? So this is du now. By the way, you don't have to do all of this when you're actually evaluating the integral. I just think it's useful for me. Oh, this is bad. Let me see if I can fix the... I don't think I have any control over... Ooh. I don't think I have any control over the brightness. I need to get a better dot cam, I think. Well, anyway, hopefully you can see what I've written there. But anyway, you don't need to circle all this stuff. I'm just doing it just to make sure that we're all on the same page in terms of U substitution. Anyway, so 2 and dx, that's going to be replaced with du now, and 4 plus 2x, that's going to be replaced with just u. Okay, not you, the person that I'm talking to, the letter U, right? Okay, so here's what we get when we make all those replacements. We're going to have 3 halves times the integral of square root of u du. And that's that, right? That's all there is to it. From there, it's pretty simple. Square root of u is just u to the 1/2 power. So we're going to add 1 to the exponent and then divide by that new exponent. So 1/2 plus 1 would be 3 halves. And if we divide by 3 halves, that's the same thing as multiplying by 2/3, right? So we have 2/3 u to the 3 halves. And since this is not a definite integral, don't forget you have to have your constant of integration plus c. Man, that's really terrible. Geez, I wonder if it's better if I just use black ink here so you can see what I'm writing. 3 halves times 2/3 u to the 3 halves plus c. Yeah, that's better. Why is it so dang fuzzy? Anyway, 3 halves times 2/3, those will just cancel. You get u to the 3 halves. And we can replace u now with the 4 plus 2x. So it's just 4 plus 2x to the 3 halves plus c. Right, and that's that one. So that's U substitution, right? We've been doing it all semester. So I'm not going to, the rest of the U substitutions I'm not going to do in quite that amount of detail. But let's look at another one. Let's do integral of 4x tangent x squared dx. I'm just going to stick to my black ink because it's showing up better here. Okay. Unless maybe I can change. No, that doesn't help. Well, I don't want to waste your time sitting here trying to figure this out. So anyway, actually, let me pause the video and see if I can. Let me pause the recording, and I'll see if I can figure. Yeah, okay. I think I figured it out. I think I figured out how to like get it to focus a little bit better, and you can see the colors kind of showing up a little better now. Anyway, so let's do this one. So this is going to be another U sub, I think, right? Because notice the idea behind U substitution is you're going to let U be something so that the derivative of whatever you're letting U be is sitting somewhere in the integral. And in this case, if I let U be x squared, derivative is 2x. And I've got something close to that sitting out right there. So I'm going to say let U be x squared, then du is 2x dx. And I can fix up this integral so that, first of all, if I take out the 4, then I've got, and if I make it a 2x, I've got to offset that with a 2 there, right? So then I've got 2x tangent x squared dx. That's going to now become 4 divided by 2 is 2. So this is going to become 2 times the integral of tangent u du, right? The du takes care of the 2x dx, right? So we've just got tangent u du. So now we just have to remember what the integral of tangent u is. And so you should remember from your previous, oh goodness, that's still bad. But you should remember from your previous calculus classes that integral of tangent u is negative natural log of the absolute value of cosine u. Okay, so this would be negative 2 times the natural log of the absolute value of cosine u plus c. And the reason for that, by the way, is because you could do another like u substitution, although you'd have to call it like a w substitution this time, I suppose. But just say tangent u is sine over cosine, and then let w be cosine u, right? And then you end up with this thing. But yeah, so that's that. Of course, we want to describe this in terms of x, since the original problem was stated in terms of x. So we're just going to replace the u and back substitute and put it in an x squared. So this is negative 2 ln of cosine of x squared. And that's that one. Okay? Let's do another one. Let's do integral of 1 over 9 plus 4x squared dx. Okay. So here's the deal with these kinds of things. First of all, you should probably recognize right off the bat that this is going to be a tangent inverse type of situation, right? So this is a tangent inverse type of situation. But in order to get it to fit the bill, you have to have a variable squared. And here we have a constant times a variable squared. So the way that you can kind of fix that up is, first of all, we can think of this, instead of thinking of it as 4 times x squared, we can think of it as the quantity 2x squared, right? And then you can do a little u substitution. You can say let u be 2x, and so then you'll just have a u squared there, right? So that's what I'm going to do. I'm going to do u substitution. I mean, first of all, maybe I'll say this. This is 1 over 3 squared plus 2x squared dx. That makes it a little more obvious that, oh, okay, yeah, this is an a squared plus u squared situation. I just need to let u be 2x, right? And then du is going to be 2 dx. Now, I don't have a 2 dx, I have a 1 dx. But I can force it to be a 2 as long as I put a 1/2 out there, right? Then I've got du. And so this whole integral is going to become 1/2 times the integral of du over 3 squared plus u squared. And there you go, right? That's a tangent inverse. This is going to be 1/2 tangent inverse. Oh, I'm sorry. No, I was missing the 1 over a, right? So this is like in our little formula, this is a, so I have to multiply it by 1/3. So it's actually 1/2 times 1/3, right? 1 over that number, and then the tangent inverse of u over a. Okay? So that's that idea there. And of course, we can replace the u with 2x now and go ahead and multiply that. So we get 1/6 tangent inverse of 2/3 x plus c. Or you could call it 2x over 3 or whatever, but that's that. Okay. Let's do another one. See if I can fit one more on this page. Let's do integral of secant ln of x tangent ln of x over x. That looks scary at first, but it's not bad. It's not bad. Because you'll notice that with a clever u substitution, this is actually really easy. If you let u be natural log of x, then du is going to be 1 over x dx, right? So it's going to be this thing, this 1 over x dx. That whole thing is going to be du. And you're just going to have secant u tangent u, right? So let u be ln of x. Then du is 1 over x dx. And we end up with integral of secant u tangent u du. So now you just have to remember, wait, what's the integral of secant tangent? And the answer is it's just secant, right? This is just secant u plus c. Right? So that's the easiest one so far. Of course, we can back substitute now and call this secant of ln of x plus c. And by the way, it's never a bad idea to check your work by differentiating, right? So if you take the derivative of this thing, well, you should end up back here, right? And sure enough, right, derivative of secant is secant tangent. So derivative of this would be secant ln of x times tangent of ln of x times the derivative of ln of x, which is 1 over x. And boom, you end up back where you started. So that's good. Moving on. Let's do another one. Let's do integral of e to the tangent inverse of x over 1 plus x squared. Oh, this is almost pointless given what we just did, right? It's like, oh, it's the same kind of situation as what we just saw. Although, you might be fooled into thinking, oh, this is a tangent inverse form, right? It's 1 plus x squared in the denominator, so it seems like it's going to be a tangent inverse. But once you do the u substitution, you'll see that actually that doesn't work. I've got this annoying little fruit fly swirling around my face. Anyway, notice that you've got to take care of this tangent inverse of x somehow. This is in the exponent of e, by the way, so it's e to this power. Well, notice if I let that exponent be u, what is the derivative of tangent inverse? Well, derivative of tangent inverse is 1 over 1 plus x squared. Ah, there it is, right? So in other words, the 1 over 1 plus x squared dx, that's just going to be replaced with du. So I'm just going to get e to the u, right? So let u be tangent inverse of x. Then du is 1 over 1 plus x squared dx. And we get the integral of e to the u du. it just simplifies all the way down to there. Integral of e to the x is, again, you should just know that that's e to the x, or in this case, e to the u, I suppose, plus c. And so that would be, if I replace u with tangent inverse of x, it would be e to the tangent inverse of x plus c. Okay, and that's all there is to that one. Okay, two more examples, and they're very closely related to each other, but I think they're interesting to look at kind of back to back. So let's do it. Let's do integral of x cubed over square root of 1 minus x to the fourth dx. Okay. So here, I think if we let u be 1 minus x to the fourth, then du is going to be negative 4x cubed, right? Which I basically have up here. So that's not a bad plan, right? Okay, so I can give myself a negative 4 there, as long as I offset it with a negative 1/4 there. Okay, and so then this integral is going to become negative 1/4 times the integral of negative 4x cubed dx is just going to be du. So it looks like this is 1 over the square root of, this was u. Okay, so it's just 1 over square root of u. All right, that's u to the negative 1/2. So I add 1 to the exponent, I'm going to get a positive 1/2. Then I divide by that new exponent. Dividing by 1/2 is the same as multiplying by 2. So I'm going to get a negative 1/4 times 2u to the 1/2. Negative 1/4 plus c. Okay, negative 1/4 plus, or times 2 is negative 1/2. So I'm going to get negative 1/2. U I can replace with 1 minus x to the fourth, and raising that to the 1/2 power is the same thing as taking the square root. So I'm going to do square root of 1 minus x to the fourth power plus c. Okay. And there's that one. Okay, now let's look at one that's very similar to it, and this will be our last example. Okay, let's say you've got the integral of x over square root 1 minus x to the fourth. Okay, so you'll notice the only difference between this example and the previous one is that in the previous one it was x cubed in the numerator. Now here it's just x to the first power in the numerator. But I think the result ends up being pretty drastically different. Now there are, if you look at this, this is a difference of squares. You could factor it as 1 plus x squared times 1 minus x squared. And that might lead you down a path that, could be useful potentially. I don't really know, because I haven't explored it in that way. So, and in general it is a good thing to kind of point out that, don't forget that you also have algebraic techniques that you can use. You have some algebra that you can use to fix stuff up, if it's helpful. But that's not how I'm going to do this one. What I notice is that I have a square root of 1 minus something squared, right? If I think of this as x squared, then I have 1 minus something squared. I have square root of 1 minus something squared. So that is like a sine inverse type of situation, right? The only problem is that with a sine inverse, you usually just have a constant up here, and we have a variable. However, notice that the variable down here that's being squared is x squared. And when I take the derivative of x squared, I get 2x. Ooh. So if I do a u substitution first, then I think I can get this to be a sine inverse type of thing. So, so first of all, notice that this is the integral of x over square root of 1 minus x squared squared. And now let u be x squared. Right? Then du is 2x dx. Okay, so I need a 2x dx. So I offset that with the 1/2 there. And there it is, right? So I can replace the 2x dx with a du, and I can replace the x squared with a u. So I'm going to get 1/2 times the integral of 1 over square root of 1 minus u squared du. Right? Well, 1 over square root of 1 minus u squared, so a in this case is just 1. So this is going to be sine inverse, 1/2. So I have to have the 1/2 from the beginning, but it's 1/2 times sine inverse of u over a plus c. All right, so that's 1/2 sine inverse of u, which was x squared, plus c. Okay, so very different result, right? Very different result from what we had before. But that's that one. Okay. Anyway, so hopefully that's helpful. Again, this was all just review, so nothing new in this section. But you'll have an opportunity in the homework to practice some stuff and sort of bring your chops back up to speed with some more difficult integrations than what we've been dealing with so far this semester.